announcements. So one thing is that in this season, the committee decided that global Poisson will be once in 2 weeks. That's why there are many activities which now take place in physical presence. And I think people felt that every week this is too big a constraint, that it's in some way too much in this post-COVID era. And the other thing is, so every 2 weeks, which means that next time it will be normally October 6th, but we don't yet have a speaker. We don't have a confirmed speaker, so we will keep you updated. And after that, I think there is a planning more or less till the end, or almost till the end of 2022. So with that, let me introduce the speaker of today. It's Pedram Hekmati, who is normally in Auckland, but now we're lucky that he is in Europe, and that's why he agreed to speak without 12 hours time difference, which would be usual otherwise. And his topic is equivariant index on toric K contact manifolds. Pedram, I give you the floor.
Thank you so much, Anton. Yeah, so first of all, thanks to the organizers for inviting me to speak. And for everyone for showing up. I have to say I'm looking forward to actually watching some of these seminars live now that I'm in Europe. So previously it was 3 a.m. or 5 a.m. in the morning. So yeah, I want to talk about a project with a PhD student of mine, Marcos Orseli, that we're hopefully about to wrap up. And it concerns it's pretty much an index calculation, but on these particular manifolds, toric K contact. So So the outline of my talk is I'll give a little bit of overview of toric contact geometry and state some classification results about such manifolds. Say very briefly what the notion of equivariant index is for this particular operator that we are interested in, and then the last part of the talk is pretty much the calculation, which is I should say off the bat is pretty much it's a result of ATIA that is sort of very nicely suited for this particular geometry. So I'll explain sort of ATIA's general results, and if you apply it to this particular setting, you get quite explicit formula. So that's what sort of kindled our interest in this problem. All right, so assuming not everyone perhaps thinks about contact manifold every day, I'll give you some definitions. So yeah, contact manifold is a odd dimension manifold with a maximally non-integrable hyperplane distribution. So typically that you can define that in terms of the kernel of a contact one form that is has property that it's differential restricted to this distribution, is non-degenerate, so it gives you a symplectic structure on the transversely. And a contact form also singles out a distinguished vector field, no vanishing vector field called the Reeb vector field. It's defined by the conditions that if you contract with the contact form, you get 1, and if you contract with the differential of the contact form, you get 0. And what does it mean to be toric? Well, if your manifold is 2n plus 1 dimensional, if it carries the effective action of n plus 1 dimensional torus, preserving the contact form, then it's a toric contact manifold. You can just by averaging of the group always find such an invariant form. And we say that it's of Reeb type if the Reeb vector field is generated by an element in the Lie algebra of the torus. So there is one-to-one correspondence between contact manifolds and symplectic cones. So if you think of contact manifolds in terms of their cone, then this is the usual notion of a toric structure in the symplectic setting, but now in the compact case, non-compact case. So given a contact form, there's also a moment map for this torus action defined by this equation, and you can also associate the moment cone to your contact, toric contact structure. So it's defined by taking the image of this alpha moment map and then just sort of taking rays out from the origin at every point. And now what's very nice about these toric contact manifolds is that they admit a very sort of beautiful classification, much like the toric symplectic case. And so the several people working on the classification of toric contact manifolds, but it was completed by Eugene Lerman. And I'll just give you briefly what the classification says. So essentially, toric contact manifolds fall into two groups. Reeb type are the ones where the Reeb vector field is generated by an element of the torus, Lie algebra of the torus, and then there's also a class that are not a Reeb type. So I have to introduce a little bit of notation. If ZT is the integral lattice of your torus, then it turns out the Reeb type toric contact manifolds are classified by the image of the moment map, much like the toric symplectic case, but there's some conditions on what kind of cones are allowed. So this condition was introduced by Lerman. So a cone is good if you have a minimal set of primitive vectors in this integral lattice, such that well, two conditions. One is that essentially saying that you have a polyhedral cone, so it's a cone over a polytope, and the second condition is that you have exactly k facets. If you look at the intersection of exactly k facets, the normals can be completed into an integral base of your integral lattice. So if you think of these vectors as a k times r, k times n matrix, then it can be completed to n by n matrix inside the SLNZ. All right, so with this condition on, and the goodness condition has to do with the construction of this Reeb type contact manifolds is done by Delzon type construction, and the goodness ensures that you get a smooth quotient. All right, so the theorem is if you have a toric contact manifold Reeb type, then the moment cone, or if you pick a contact one form for your contact distribution, it has to be a strictly convex good cone. So strictly convex is that it doesn't have any positive dimensional linear subspaces, this cone. If you fix your alpha, then this the image of your alpha moment map is compact convex simple polytope. So you get it by taking an intersection of the hyperplane defined by the vector that's generating your Reeb vector field with your cone. So you have your moment cone, and then once you pick your contact one from alpha, that gives you a Reeb vector field, and that gives you a hyperplane that slices this cone, and that's the polygon. And essentially Lemmer's classification says that establishes the converse of this, that given any strictly convex good cone, you can construct an associated toric contact manifold with Reeb type. All right, so now this particular toric manifolds have this nice combinatorial description. So it is natural to try to understand the properties from their combinatorial data, so the cone in particular. And that's indeed true. So there are a couple of results here that I listed. One is concerns a fundamental group of these toric contact manifolds of Reeb type. So unlike the toric symplectic cases, they're not simply connected in general, but their fundamental group can be described in terms of quotient your integral lattice by the sublattice generated by the primitive integral normals to the facets of your cone. And this quotient is in fact a finite cyclic group. You can write down the order of the cyclic group in terms of the normals, the determinant of the normals. And similarly, you can describe the second homotopic groups in terms of information from the moment cone. And also there's work by Liu on characterizing the singular and equivariant cohomology of good toric contact manifolds. again, using combinatorial data of your cone. So that's the general theme. And sort of the index problem I want to discuss is also there's a natural operator on these manifolds whose index you can consider, and whether you can connect it directly to the cone. And that's essentially the result I want to mention. But just before I move on, let's just talk about non-Reeb type. Let me just say that even the non-Reeb types are, at least the diffeomorphism type of those manifolds are completely understood. And this is the list of the various non-Reeb type toric contact manifolds that exist out there. And as you see for the fundamental group, most of them you can just read off immediately. The non-trivial case is the third case when it's the principal T3 bundle over the two sphere. And there again, you can use some exact sequences to compute what that is. And again, it's two copies of Z, and a cyclic group whose order is determined by the chunk class of your T3 bundle. The contact structure, of course, is requires more information to describe those. So unlike the Reeb type, these are not in general described by their, or like they're not classified by their image of their moment maps. So in the fifth case, for instance, the image could be the entire dual torus. So it wouldn't tell you distinguish them apart, tell them apart. All right, so a few more definitions. So you can also equip your manifold with the metric structure, and if the metric is chosen such that the Reeb vector field is a killing vector field, then it's called K-contact, and you can show that what it gives you is gives you an almost complex structure on the horizontal distribution. And if that almost complex structure is integrable, then you get what's called a Sasakian structure on your manifold. So the Sasakians are transverse scalar, or if you like, they're another way of saying that is say that the metric cone is a scalar manifold. And one more thing to say about this isometries generated by the Reeb vector field is that you can get to two different situations. One is that the flow of the Reeb vector fields close up to circles, so they act locally freely on your manifold. These are called the quasi-regular K-contact manifolds, and if the closure of this one parameter subgroup is the torus of rank 2 or higher, then it's called an irregular foliation. It gives you an irregular foliation, so it's an irregular K-contact structure. And now you can add, this is in general, not necessarily assuming toric, but it turns out in the toric case, at least when you work with Reeb type, every toric contact manifold Reeb type actually admits an invariant K-contact structure. And in fact, you can always choose your metric structure to get a compatible Sasakian structure. So in general, this is an interesting problem, whether every K-contact manifold admits a Sasakian structure. So that's not true in general, the abstractions, but in the toric case, all of these sort of coincide. So we can sort of use that in our case, since we're looking at compact toric manifolds of Reeb type. We can assume that we pick a metric structure that is Sasakian, so that we get an integrable transverse scalar structure on our manifolds. All right, so let me give a couple of examples. So these are the easy ones. Obviously, the sphere, the odd sphere, has a natural contact structure. The contact form is, you can write it in Cn+1 and just restricted to the sphere. And in this case, this is the standard contact structure. So the Reeb has completely periodic orbits. And of course, this is nothing but the Hopf vibration over CP2n. So this is a special case of what's called a Bout-Wang vibration. So given any symplectic manifold with a symplectic form with integral periods, you can construct a circle bundle over it, and you can prove that there exists a connection whose curvature is your symplectic form, and the connector is in fact gives you a contact structure. And if you start with a toric symplectic base described by an integral Delzant polytope, then the associated cone will be exactly the contact structure would be toric, and it's moment cone would be exactly the cone over this Delzon polytope. So this example of a sphere again is one of these exactly of this type, because CPN has a, oh sorry, I meant CPN, not CP2N. CPN has a toric structure, and associated Buchmann fibration has acquires a toric structure as well. All right, so these are the sort of, this corresponds to the case when the Reeb flow acts actually freely. A more interesting classical example would be if it's quasi-regular, where the base is a Kähler orbifold. So in that case, you could take one of these Delzon polytopes with labels, as shown by Lerman and Tolman, that these classify the toric Kähler orbifolds, and then you get an orbifold circle bundle, would give you one of these quasi-regular toric contact manifolds of Reeb type. And there are many examples of completely irregular toric structures, but in fact, it turns out you can always deform or perturb your contact form in the Reeb toric case of Reeb type, so that you get a quasi-regular Sasakian structure. All right, so that was the background on toric geometry. Any comments or questions? All right, if not, what I want to do is then to discuss another sort of natural complex one can associate to one of these manifolds. More generally, on a Sasakian manifold, there's a notion of horizontal differential forms, and since you also have a transverse complex structure, you can split your complex in the usual way into the horizontal Dolbeault. And in the Sasakian case, you can always pick sort of adapted coordinates so that the Reeb vector field is just DDR in the first coordinate, and the Dolbeault operator looks locally as written, d psi bar I contracted with d psi I. So that's the sort of local structure of this Dolbeault complex. And more generally, you can also, if you have a foliated bundle in manifold, you can also twist your Dolbeault complex by this auxiliary bundle. All right, so this is an example of a complex that is not elliptic. Its symbol is not elliptic, but it's elliptic transverse to the Reeb foliation. So we're interested in computing the index of this operator in the toric K contact case. So let me just review a few definitions. So what does it mean to be a transverse elliptic operator? So first of all, being elliptic means that the symbol of your complex is an isomorphism away from the zero section. But Atiyah and Singer, they generalized this notion vastly to a situation where if you have a group action, then your operator is only elliptic perpendicular to the orbits of the group action. So that's justified as this first definition. You have this subspace of your cotangent bundle, which is exactly the vectors that vanish in the direction of the orbit of your group action. So G here should be a T. So I'm restricting everything to the torus. I mean, this is of course true for any compact Lie group. And then we say that a T-invariant pseudodifferential operator is transverse elliptic if its symbol is invertible, not on Tm, but on this subspace TTM, away from the zero section of that. So there's still a natural projection from T star Tm to the base. And the equivariant index of this operator is then defined as the character of the group because the group acts on the kernel and co-kernels, you can compute its character. So the equivariant index, the way we want to define it, is exactly as the difference of the character on the kernel of this operator minus the kernel of its adjoint. Now in the elliptic case, this makes sense, as the kernel of the operator would be Fredholm, and the kernel and co-kernel would be finite dimensional. So this would be an element in the representation ring of the torus in this case. But in this transversal elliptic setting, this is the operator is not Fredholm, so the kernel and co-kernel in general are infinite dimensional. But what you can do is that you can still decompose these spaces into isotypic components for your group action. And what Atiyah showed is that these irreducible representations actually only show will only occur with finite multiplicity, and the growth rate is such that this infinite sum that you have actually defines the distribution on your group, so the torus in this case. So the index does make sense, but in a distributional sense. And he went further to prove that the symbol actually defines is a well-defined class in the equivariant K-theory of TTM. Here I'm identifying the tangent bundle with the cotangent bundle. And in fact, the index only depends on the symbol class, not on the operator itself. So we have a well-defined sort of map from the equivariant K-theory of TTM to distribution on the torus. So the problem at hand in this abelian case is to compute the index of the symbol of the Dolbeault operator, or the twisted Dolbeault operator that is horizontal on a toric K contact manifold. So that's kind of the problem we're interested in. So there's this fun example in Atiyah. So I thought just to give you an example of this toric index, this transverse elliptic index works. Here's a very simple example. You consider the circle acting on itself by translation. And then you take the zero operator, which sends smooth function in the circle to zero. So since you're acting by rotational action, this TS1 S1 in this case is zero, since the orbit just collapses to one point. So the action, so this operator is by the definition in the previous slide, is an transversal elliptic operator, zero operator, with respect to the circle action, but it's certainly not Fredholm. And now you can decompose this the space of smooth function in Fourier modes, and you get with multiplicity 1. So the index, the equivariant index of this transverse elliptic operator is just a sum of t to the k over all the integers, which is nothing but the delta distribution, so supported at the unit of the group. So this is just goes to show how in this very simple example how you get a distribution out of the equivariant index. And in fact, this example is quite relevant to the general index calculation for toric K contact. All right, so let me, just before going into a bit more detail about the operator and the index calculation, let me just say a few words about motivation for this problem. So there's work done in the physics community where you have obviously partition functions for interesting gauge theories, and if you perturb, sort of, you've modified the Lagranges in an appropriate way, you could get BRST exact partition functions, so they're susceptible to localization. And this was in particular on the force sphere, this was initiated by Pestun, and in the 5-dimensional case, Maxime Zabzin and his collaborators have done a lot of calculations where they're able to compute these perturbative part of the partition function. So essentially, the calculation boils down to computing a determinant, and the determinant is computed by knowing the weights and multiplicity of the torus action on, or the group action in general on the kernel and co-kernel of a certain operator. If you're in the Sasakian case, the operator turns out to be exactly this Dolbeault operator. It's horizontal Dolbeault. So by computing the index, you obtain the information about the weights and the multiplicities, and then you can repackage that into the evaluation of the determinant that comes out from this localization calculation of the partition functions. So one motivation for trying to understand this particular index is from these partition function calculations. I'm being somewhat hand-wavy because it takes a lot of time to explain it, and in fact I'm not entirely sure how the whole business works. So should ask Maxime to give a talk and explain it to us. but another thing that happens from this partition function is that they localize on certain sort of classical solutions, and in the 5-dimensional case, if I extend to higher dimensions, you get what are called these contact instanton equations, in fact, you can put any gauge theory on a foliation. So this story, even though we were looking at this contact instanton that came from this partition function calculation, you could also look at other gauge theories like cyberbreathing theory. And what happens is that if you linearize these equations, they give you the deformation complex to give you the dimension of the moduli spaces. These are computed by these particular transverse elliptic operators. So that's another motivation for wanting to get a hold of the precise sort of index formula for this complex. And more generally, just from index theory perspective, this is sort of the odd dimension analog of this same problem done for toric manifolds. All right, so these are a few reasons why you want to compute this thing. And let me just say that I'll present some formulas for what the index should be, but these kind of techniques, the technique that we are using is pretty much the technique that Attia has laid out in his book, and also been employed by these different communities computing, in particular, partition functions. So they definitely mastered the art of computing this index. What we didn't understand when we were trying to read these papers was a little bit more precisely how you read off these isotropy weights, and then try to get a more manageable formula for the index. So I just want to say that there are instances of this formula I'm about to show already known in the literature and probably by experts. So, but our aim was to try to actually push the calculation all the way to the end in the most general setting that where this technique was applicable. All right. So okay. So essentially, the result we have is that if you have a toric Sasakian manifold, then you get, and you have an equivariant, you can also twist your Dolbeault operator by an equivariant vector bundle, then the equivariant index becomes something that looks very much like the Attia-Bot's Lefschetz fixed point theorem. So the ingredients are, you get the character of your vector bundle restricted to isolated Reeb orbits corresponding to the edges of your moment cone. And then you get some contribution from the Reeb, the circle action on the orbits themselves, which is embedded circles, and that's what gives you these delta functions. If you remember from the zero operator, we got something like 1 minus t. Delta of 1 minus t is exactly related to that calculation. And then, as usual, you need a contribution from the Tom class of the equivariant Tom class of the normal bundle, is when you go from the local to we globalize your local index calculations, and this is exactly what you have in the denominator. It's essentially the contribution from the equivariant bot class. The difficulty here now is that since you work with transverse elliptic operators, as you map them into your space, you have to do some deformation, and that's why you get these rational functions. And the sign up here in the exponent has to do with how you expand these rational function. Whether you expand it, the plus means you expand the Lorentz series at infinity, and minus means you expand it at the origin. So this is again in contrast to the calculation in the symplectic case. There you would get the equivariant Euler class in the denominator, and then if in the toric case you can pick, there's a program for picking polarization vector and expanding depending on the sign of the inner product between the polarization vector and your isotropy weights. In this calculation, the deformation you need to do to get this formula already involves a polarization vector. So that's why it's already showing up in the exponents.
Pedram?
Yes.
May I ask you, so this delta function in the numerator, that's
yes.
like in the ATS example that you showed before, yes. Right? That has the same origin, is it right?
Exactly the same origin, yeah. I'll get to some of the steps in the calculation.
Okay, thank you.
The only reason you get this extra mu L is that you have a you have your embedded circle. So when you act with the circle, it's the weight of the circle action in the orbit direction. So
okay, thank you.
Yeah, but that's exactly it. Yeah. And then if you don't have, you just take the untwisted Dolbeault operator. So that would be like the fundamental cycle for your toric manifold. Then you get this this sort of lattice point formula. So I want to say a few words about how you get this from this more general formula. Again, this is reminiscent of what you get in the symplectic world. The only difference is that now you're summing over lattice points of the cone, and you also need to sum over the lattice points of the interior lattice points of the negative cone. And at this stage, let me just also say that there is a formula. There's a paper on toric Sasaki manifold by Martelli, Sparks, and Yao, where they computed the volume of the Sasaki manifold in terms of this kind of lattice point formula. And as you see, this expression I'm written down at the bottom of the page is exactly the first term in the index. So it's not entirely clear if we do similar kind of limiting calculation of the index, whether the contributions of the negative cone goes away. Essentially, the lattice point formula for the volume of your toric Sasaki manifold is a truncated cone. So you have your cone emanating from the origin, and the volume corresponds to sort of a pyramid sitting over the origin, counting the lattice points. That's what the formula is. So, so this is what this limiting procedure is doing. So it would be I don't know, maybe someone expert in the audience can immediately see how you would compute the volume directly from the equivariant index. So either it's the same limiting procedure and the contribution of the interior of the negative cone just go away, or you might have to do some other limiting procedure to get the lattice point of the truncated cone. Right, so essentially what I want to do in the remaining time is to outline the steps for getting these two formulas. Again, as I said, there's as usual in index theory, there might be many different ways of arriving at the same formula. So the idea our technique is to essentially just follow the recipe in Attia's book and then try to get all the way down to as explicit formula as possible. And this is also the approach a lot of these physics papers that are taking. So our goal was to try to understand exactly how they do these calculations, but as precisely as possible. But let me just point out a couple of things here. There are other techniques that might give you the same results. Obviously, there's a very beautiful homological formula for transverse elliptic operators in much more general setting by Michel Verne and with Paradon and Byrne. The difficulty there is that you sort of you have to integrate over equivariant characters classes over open manifolds, but it's not unreasonable that in this particular geometry you would be able to get similar formulas from their cohomological formula for the transverse elliptic index. Another thing I should say is that I mentioned that in this toric Sasaki case, you can always perturb your contact form to get a quasi-regular toric Sasaki structure, which means that it's essentially an orbifold circle bundle over a Kähler orbifold. So in principle, one should be able to also compute this through a Kawasaki orbifold index theorem, and then using the description of the toric Kähler orbifold in terms of these labeled polytopes.
Pedram, since you mentioned Berlin-Verne, there's this formula also of Sean Fitzpatrick from many years ago. Do you know this one?
I did know. I know of Sean's. Yes, there is. I don't know if that did he do the toric case or
no, not. He did case of G actions on contact manifolds where the G action is transverse to the hyperplane distribution.
Right.
In that sense, it's more general, I suppose. And the point was exactly that he reformulated the Berlin-Verne formula in such a way that you end up with an integration over the manifold M, over the finite dimensional, or the manifold M itself.
Okay, so that might also be an avenue for getting this formula. Also, in the Poisson conference in July, Yanis gave a very nice talk where they all get working much more generally with transverse symplectic foliations. with the infinitesimal Lie algebra action. My understanding that I think Yannis mentioned at the end of his talk the K-contact calculation as a special case of their index theorem. I think I don't remember exactly what all the ingredients were in Yannis' talk, but I think the operator they were considering was sort of the basic Dolbeault operator. So that would correspond to the invariant part of this index, because if I remember correctly, the index they got was an element in the representation ring, not a distribution. So I don't know if Yannis is here, how he could correct me if I'm mistaken. All right, so this is one of these things where there's a lot of details to give, and experts know it better than I do, and those who don't know this stuff I might lose you. So feel free to interrupt, and I might go through this relatively quickly just to give you sort of the basic ideas behind it. So essentially, Atiyah has solved this index problem for transverse elliptic operator when you have a torus action. But it's solved in a sort of algorithmic way, so to speak. So essentially, I'm going to explain his algorithm and then say how in this particular geometry you can successfully apply it to get quite concrete formulas for the index. So so again, if you have a T action in a manifold, there's a natural filtration with respect to the size of the isotropic group of your torus action. And Atiyah also showed that this gives rise to a sequence of split exact sequences. So essentially, you restrict. This is sort of a localization procedure. You restrict your tangent bundle TT to your manifold, where you excise some part of these from this filtration, and then you want to relate the index recursively to the index in that you're actually interested in, which lives in this KT of TTM. So essentially, if you take this short exact sequences and iteratively apply them, what this tells you is that the symbol in KT-TTM is really computed from symbols in these there's like smaller K groups of the smaller spaces, but then you need these splitting maps, which are choices that you're making in order to assemble all these various contributions to get the full index. And moreover, this TTM restricted to mi plus 1 is a complex vector bundle of a TT of mi minus mi plus 1. So it's you can apply the Thom isomorphism to write this equality as well in the second line here. It's difficult when you don't have a pointer. So all right, so essentially what this tells us is that if you have a symbol class in KTT of TTM, that should be X should be M, then the index is obtained by computing the indices of these local contributions. Okay, so in general, in this sense, you solve the index problem if you can pick a nice sort of stratification of your space where you can actually read off the index contribution from these smaller small pieces. And I guess maybe the moral of the story here is that in this toric contact case, you can deform your symbol so that the contribution is only localized to the edges of your moment cone. So just based on Atiyah's description, we sort of you can easily show that there's a sort of a characterizing property for deforming your symbol complex, such that the contribution only comes from MJ and higher. So you kill all of the contribution from the filtration of degree I and less. So this you can achieve if you can find a vector field, we call it VPerp, such that you see in the first line, you deform your symbol complex in the direction of VPerp, such that it becomes an isomorphism for every X in M tech MJ. And you also do two other conditions, is that this vector field is tangent to the orbit, and it vanishes if and only if you're at the point inside MJ. So essentially what this does is that it localizes it forces this deformed symbol when you move it along the VPerp to become an isomorphism on all these lower parts of the filtration. And in this Toric-Sasaki case, you can construct one of these vector fields so that it kills off everything except in filtration degree n. So remember, you have this filtration degree, and in our case, mn plus 2 is 0, and mn is actually ns plus 1, since we have an effective torus action, is also 0. So if you can achieve this deformation, then so that you only get index contribution from j equals n, then you're done. Because, all right, so let me say a few words about how you get this deformation vector. So the idea is that you want to get a vector field so that when you do this deformation of the symbol complex, your contribution only localizes to mn. Mn in this filtration are exactly the isolated closed orbits corresponding to the edges of your moment cone. Here. So the idea is that since we have a toric contact manifold Reeb type, you know that the Reeb vector field is generated by an element in the Lie algebra. And moreover, we know that at every closed orbit corresponding to one of these edges, we have the cone normals, let's denote them VLI. So we need to index it for every orbit, you get different normals. So we need to keep track of which orbit we're working at. And then the good cone condition, this is this condition that you can always take if you have a subset of these normals, you can always extend it to an integral basis. That was a good cone condition. It ensures that there exists a vector V0 in your integral lattice such that you get an integral basis if your weight lattice of your lattice. And in particular, you get a dual basis, which you denote mu L. These are related, will be related to the isotropy weights, as we'll see, after your torus action. For the dual lattice, the weight lattice. All right, and essentially we want to build this vector field as a linear combination of Reeb and the vector field generated by these normals. So first, this calculation in the middle is just ensuring that if you pick your normal vectors and then together with a Reeb vector, this is actually a basis, not necessarily not the integral basis, but just a basis for your Lie algebra T. All right, so to get this deformation vector, you pick some arbitrary vector in your torus, and then what we want to do is that we want to shrink away the Reeb contribution as you approach each orbit. All right, so that's essentially what's happening in this slide. Is if you look at the middle, the V perp is you take your arbitrary vector V, so it gives you vector field in your manifold, and then you pick bump functions so that as you approach each closed orbit Li corresponding to an edge, you subtract away this coefficient, which remember is the coefficient in front of Reeb, the Reeb vector field. So this deformation vector field does the job. Almost, you also need to ensure that all of these other coefficients, if I go back again here, in front of V1 to Vn, these are also non-vanishing. But these just define finite many hyperplanes in the Lie algebra, so you can always find a vector away from these hyperplanes that satisfy this condition. So, all right. So the result is that if you pick this particular deformation vector, then it does the job. It satisfies the hypothesis about lemma that the symbol, when deformed along this vector field, will only localize onto the closed Reeb orbits. And so again, if you remember, the index formula can be written as the index can be written as indices of these local contributions, and the local contribution in this case just become a standard over edges of your moment cone. So what's left to do is to just compute what these are. And again, this goes back to, I think, Anton's remark, is how you get this contribution of the circle. So essentially at each orbit, the torus splits into the circle direction that acts in the Reeb along the closed Reeb orbit, and then you have the isotropy group. And since your closed orbits are embedded circles, the normal bundle is just a trivial, it's a copy, it's a circle, so it's the normal bundle is a trivial complex vector bundle. And then you can check that if you restrict your Dolbeault operator to each of these orbits, then it essentially becomes the symbol of the zero operator. So this is this calculation of that toy example of computing the index of the zero operator. So if you maybe just move all the way to the bottom of the page, you see that the index of this local contribution splits into three parts. One is the index of this zero operator. If you have a twisted Dolbeault, then you also get the character of your vector bundle. And then what happens with is that when you restrict your operator, you get the zero operator, but then you need to map it back into your space to get a global. Right, so this procedure mapping your index country into the space is essentially done by the Thom isomorphism. So I wrote it as a product formula. So you take the normal bundle inside your space. A priori, you might have to you think of it as a tubular neighborhood of your orbit, and the Thom isomorphism tells you that this map corresponds to multiplication by this bot class. And then just by using excision, you can map it into the entire space. So there's one more step here after doing this. So essentially, the bottom line is that this index problem becomes a problem of computing these local contributions. The index of the zero operator is just that delta function we saw before, 1 minus t, now up to the power of some weight. You have the character of your equivariant vector bundle. And then you have this index of this sort of bot elements that are sort of deformed along the direction of your deformation vector. And again, this has all been done by Atiyah already. So Atiyah had computed this index computation of this deformed bot classes, and it's given by exactly the denominator in the index formula. Right, so these are the isotropy weights of your isotropy group acting on the fiber of the normal bundle. And here you see that since there's more to say here, I'm trying to say just the relevant things here. But essentially, the problem is that this Dolbeault operator, the reason you get these distributions is that when you extend these operators from the orbit to a tubular neighborhood of the orbit, you want them to define when you restrict them to this TT, this tangent bundle, the subspace of the tangent bundle is perpendicular to the orbits of the group. You want this to become a compactly supported symbol, and it's not. So essentially, the idea here of Atiyah is to deform these elements so that you get a well-defined K3 class, so that's the origin of this sign. As you can deform in the direction of this deform vector or in the opposite direction, so you get two different signs. And this calculation, of course, is done locally, but since we have a global deformation vector, you're going to get different signs depending on what the deformation vector looks like at each closed orbit. So I see that I have, okay, sorry, I had a message in the chat. All right, so just one more remark about this calculation is that the weights that you get from the action on the normal bundle, something that was actually confusing to us when we were trying to read the physics paper is how you relate them back to the cone. And there's a very nice description. There's a normal form theorem by Lerman in his paper that classifies toric contact manifold that actually tells you that how they connect to the edges of the as a dual basis to the normals of the facets of your cone. So maybe the remark here is that in the symplectic case, the edges, the isotropy weights generate the edges of your moment polytope. That's not the case in the toric, because as you go to different orbits, the isotropy could be of different size. So that was a bit of a mystery originally when we were trying to read this physics paper, how they're actually reading off the weights. But in fact, it's the normal form of Lerman tells you exactly how they're related to the cone. So I just want to make that distinct remark, how it sort of differs a little bit from the symplectic calculation. All right, and then the circle case gives you this delta, and put together you get this sort of Lefschetz fixed point type theorem. Instead of fixed points, now you have these edges of your moment cone. All right, at this point, any questions on? I'm not sure if.
Pedram, maybe I have a somewhat naive question. So of course it's very, very beautiful that you get the edges, right? But can one imagine some other situation where other facets would also play a role? Right here, it was very fortunate that you were able to get rid of all those other faces of other dimensions or of other codimensions of the cone, but is there some kind of maybe some other setup where they would play some role?
Yeah, I mean, the short answer is I don't know, but I think if I just go back to this lemma, yeah, you have this lemma tells you sort of what some necessary sufficient conditions at least for a deformation to kill off contribution from lower stratum. So I guess one way, it's not an answer to your question, is to find geometries where you have enough sort of freedom to construct such a deformation vector field. I mean, sort of essentially, if you want to apply this technique, it boils down to being able to suppress the contribution from these other parts of the filtration. I think what you were asking is just if there's an example of a geometry, I can tell you off the cuff, I don't know. Yeah, this is sort of the special case.
But again, maybe it's a stupid question. What if I choose some kind of wrong deformation? Right? Of course, you're now saying I can choose a good deformation which would suppress, but if I choose a bad deformation which does not suppress, would it lead to a formula which would have those other contributions that you can reshuffle eventually with good deformations?
Yes, I think that's the case. So you might be able to get the edges and maybe like some higher dimensional faces as well. Yeah, I mean that would what it would amount to. Because, you know, the isotropy, the filtration is with respect to the order of the isotropy group. So as you go up, this corresponds to different faces of your cone.
Okay, thank you.
All right, so I think I have 10 minutes left. I might be, again, testing people's patience. So what I wanted to, I got a question in the chat box. The physics papers, maybe, so Maxime Zabzin has done a lot of work on this in this area. So maybe look up Maxime on archive, I guess. Okay, great. Right, so this is the other thing I wanted to say a few words about is how in the special case when you don't have auxiliary bundle, then this index formula can actually be massaged into like where you can read off the multiplications off immediately, which is the formula in the bottom of this page. So essentially, it's just a summing over the lattice points of the cone, but you also get some of over the lattice point of the interior of the negative cone, and then you have this overall sign factor depending on the dimension of your contact manifold. So essentially, the way you get this formula is the usual polytope geometry. You decompose your formula into cones, and then you're trying to figure out a way where you get some cancellations and end up with sort of a nice useful formula. So let me be a little bit more, instead of going into every detail, let me just point out the main steps. So now if you don't have a twisting, or if you just have the Dolbeault operator itself, then this is what the index looks like. And now you can immediately expand the denominator. These are power series. It's written as rational functions, but they're actually a power series because you already have a sign assigned to them, how to expand them as Laurent series at the origin or infinity. So if you expand this, you can write this as a sum over lattice points of a cone, and the cone is written at the bottom of the page. So essentially, you have these isotropy weights give you vectors, and depending on whether you have to expand into positive or negative, depending on the sign up here, you're going to get coefficients in the non-negative reals or the positive reals. So, non-positive reals or the positive reals. So that's and then the delta function at the top that gives you the first term in this cone. So that tells you where the vertex of the cone is, and where it radiates out from. So and the sign factors come again. Remember, if you expand with a plus sign, you get a minus sign in front of the sum. So that gives you this other minus sign in front of your power series. So this is essentially the main idea. You take your formula, you expand the denominator, you get this sum of the cones, and now what we're trying to do is to get a handle of these cones to get a nice formula. And essentially the idea is to use a version of Lorentz-Verschenko to do this. And instead of going through the details of Lorentz-Vashenko, I'll just give you the basic philosophy through one example. So assume that you're tasked with a problem of counting lattice points of this quadrilateral. So what you can do is you can decompose it into cones corresponding to each vertex. You have 4 vertices. So the vertex at the origin has just summing over all the integer points of the first quadrant. And if you write that series as a rational function, that corresponds to the first rational function. And then you do the same thing with the other vertices. Each of them give you a power series, which you can, again, rewrite as a rational function. And summing these up, you have sum of 4 infinite power series, but they have cancellations because they come with signs. So in the end, the sum of these rational functions just becomes this nice polynomial in x and y. It's written in 3 rows corresponding to the 3 rows of your the lattice points in the picture. All right, so this calculation is just done by hand, but it turns out there's a way you can completely control this kind of cone expansion. So the way you do that is you pick a polarization vector psi, so it doesn't coincide with any of the edges of your polytope, and then you expand into cones depending on the inner product of your polarization vector with the edge vectors. So if the inner product is positive, you just keep that edge. If it's negative, you flip the edge and make the other edge dashed. Dash means you don't include lattice points on that edge. So again, you have 4 points, so you get 4 vertices, you get 4 different cones following this rule for whether or not to include the edges. And each of these cones, again, give you a power series in x and y. You write them out. Now you get signs also in front of them. And again, you get the same formula. But this way of doing things is a very sort of controlled way of doing cone expansions, and this is what's called the Lorentz-Vashenko formula. So instead of defining everything, since I'm running out of time, let me just, if you could look at the last line of this slide to tell you that if you have a polytope, the sum of the lattice point of this polytope can be written as sum over an alternating sum of lattice points in cones associated to the vertices of your polytope. So that's the Lorentz-Vashenko formula. But this is for a polytope, and we have a cone over a polytope. So in order to apply this theorem, we need to adapt this Lorentz-Vashenko to polyhedral cones. And that's essentially what's done in these slides that I'll spare you from. The formula you get in the end is that you take your polyhedral cone, you slice it by hyperplanes, and you apply a Lorentz-Vashenko for each hyperplane. And as you sum them up, it gives you this sum. And this looks very similar to what the index theorem ends up being. And essentially you take your this first row is what the index formula should be. So you just have to identify your deformation vector with the polarization vector. That's it. So this deformation vector in this setting is actually the same thing as the polarization vector in this Lorentz-Vashenko formula. And yeah, there are a couple of calculations there, and you get the formula at the bottom of the page, which is what we advertise. All right, so thanks for your attention.
Thanks a lot. Please, questions or comments. You can either unmute yourself or raise an electronic hand. So yeah, let me start with the following again, sort of naive question, right? You have for those 2 contributions, right? For instance, here at the bottom, there are integral points in your cone, and there are integral points in minus the interior of the cone. So could you comment, like, it's the second term is a little bit mysterious, right? Kind of what's your take at it, and why there are only 2 terms? I mean, one would think if there are many terms, then what kind of why just 2?
Right. Well, I can say a few things. And so the reason you get this negative direction comes from this delta function that you have. You have this delta coming from this, if you remember if I go back to the index formula, yeah, here, up here in the denominator. So this is what gives you this vertical direction, which forces you to not just sum over the positive cone, but also consider the negative cone. So that's the source of it. Obviously, if you twist your operator by a line bundle, the effect of the line bundle would be that an equivariant line bundle would be to sort of shift these vertices. It might be possible to get similar kind of formulas even for a twisted Dolbeault operator. But maybe just go back to where you said sort of what's going on. We found this a little bit mysterious too. I mean, I just explain where it comes from. It comes from the delta function. It forces you to sum in both positive and negative directions. There is a calculation, this volume formula that I mentioned. Let me just go back early on. Yeah, here, this calculation by Martelli, Sparks, and Yao, what they do is to consider a regular Sasaki manifold, so just a circle bundle over a Kähler base, and that they consider the Kähler cone, and then they write down the Dolbeault operator on the Kähler cone, which is not the same as this Dolbeault. So if you lift the horizontal Dolbeault to the cone, it's not exactly the same one as theirs, because it might be theirs if you take the R invariant part of that. But what they do is that they take this Cauchy-Riemann operator on the Kähler cone, and then they do a Riemann-Roch argument that since the quotient is Fano, there's no high cohomology, so the index just becomes counting holomorphic functions on the cone. And the calculation of holomorphic functions for the Dolbeault operator on the cone is exactly the first term of this index here. So that was a windy way of answering your question, Anton. But essentially, one way of understanding the first term is as the index, equivariant index of the Dolbeault operator on the Kähler cone of your Sasaki manifold, at least in the regular case where you have this Riemann-Roch argument. If it's quasi-regular, then or more irregular foliation, I'm not sure if it's you can still have the vanishing of high cohomologies or not. So that's how they then get this volume formula from that operator, which corresponds to counting holomorphic functions on the cone.
Okay, thanks a lot. More questions or comments?
I have some question.
Yes.
So I didn't understood if your D-bar operator, does it look like it has only two terms in the cohomology? If you could, you find a model on, because I know, for example, the simplest model is that if you look at modulo of Z1 square, but if you look at C2 and you look at the sphere in C2, then if you look at the corresponding transversally elliptic operators, then you get the Tm correspond to H0 and the T minus n correspond to the H1. And
Yes.
but here, so you can see very well. You can see very well this formula because your space of function is sum. I mean, your D-bar operator is
Exactly.
you have holomorphic, and until you have the H0 and the H1. So does it correspond also to something like that in all the cases? Or?
I think so. I think essentially what it is,
because here you look like you have only the term, no? Yes.
No, I think it is. I think it's related to, if I understood your example, I think it's related to that. It's just that you have several copies of that model at each orbit.
Yes, but I wonder, because you seem to have, I mean, if you look at the model, I wonder if you cannot really compute directly on the model, which is, because if I understand, I don't know the construction of Lehrman of the model of the toric variety, but can you obtain it by reduction of something, no?
Yes, I think, yes.
You just look directly on the bigger model and see these top terms, how they manage.
Right. So
I don't know. I know that I've been computing some of these things for product of when you want to construct generators of your when you want to compute generators of your MI of your H, you compute generators by splitting up your. You have to take a filtration and you split, and then you have a model. But I guess I never thought of computing each individual term in this model, but I don't know. So
yeah.
Anyway, my question is that it looks like there is only two terms.
Yes.
Which remains. Anyway, it's a nice formula.
Mm. It is,
but I wonder if you don't have, I mean, to use the filtration is a little bit annoying, huh? So I wonder if in your model you couldn't look at your global model and do some reduction on your global model. I don't know.
I think yes, it is. We followed, in our quest of understanding the physics calculations, we followed this the filtration approach. I'm almost confident you should be able to arrive at this in a different way, potentially even more in a more elegant way. The reduction is, yeah, you reduce from the standard odd sphere. That's the so potentially
because somewhat your global model that I don't understand should be nice, and maybe you can do the calculation there, and then it should be somewhat, and then you have to compute some invariants. So I don't know.
Yeah, it's certainly,
so
yeah,
I don't know.
It's feasible. I mean, I think I would need to understand how, yeah, if I want to get the cone, how to get the cone from this reduction, I guess.
But you have to get higher cohomology somewhere. So at first, it's not a positive formula, which is really nice because you have some really explicit example where your index is not positive.
Yeah, exactly.
Which is nice. Because the delta function is not a nice example. This one is very nice.
Okay, thank you. More questions or comments? Okay, thanks a lot. If there are no other questions, Pedram, thanks again.
Thanks, everyone.
Thank you very much. And so we'll keep you updated on October 6th. For sure, there is a talk planned for October 20, and for October 6th, we'll confirm to you whether we get a speaker. Okay, well, thanks a lot, and well, see you hopefully in 2 weeks, or if not,